Hello, welcome to lecture 2. Myself A. Venkat Subbareddy, Assistant Professor in the Department of Electronics and Communication, G. Pullareddy Engineering College. So, in the basic electronics engineering, in the previous lecture, we discussed about types of materials. So, in continuation with that, we will discuss about in detail about the semiconductors. So, in this session, I will discuss about the classification of semiconductors. So there are two types of semiconductors. One is called as intrinsic semiconductor and the another is eccentric semiconductor. In the eccentric semiconductor, there are two types are there. One is p-type semiconductor and the another is n-type semiconductor. So this is the energy band diagram of semiconductors. The electrons, valence electrons are available in the valency band and the free electrons are available in the conduction band, and these two bands are separated by a small gap, so which is called it as an energy gap. So this energy gap is equal to, or it is approximately equal to 1 electron volt. So in the eccentric semiconductor, a pure form of semiconductor is known as eccentric semiconductor. So at room temperature, some of the valency electron acquired sufficient energy to jump from valency band to the conduction band, becoming free electrons, also called as conduction electrons. So that is at room temperature, that is 27 degrees centigrade. Some of the electrons which are available in the valency band, so they will gain energy from this room temperature and they can jump into the conduction band, and in the conduction band they are free to move in the conduction band. So whenever electron jumps to the conduction band, a vacancy left in the valency band within the crystal, this is called as hole. So whenever the electron jumps from valency band to the conduction band, it will create one empty space, so which is called it as an hole. For every electron raised to the conduction band by external energy, there is one hole left in the valency band, creating an electron hole pair. So that is whenever any one electron is available in the conduction band, which means one vacancy or empty space is available in the valency band, and these two create one electron hole pair. Then eccentric semiconductor. So semiconductor materials do not conduct well and are of limited conductivity in their intrinsic state. So in order to improve the conductivity, so this is because of limited number of free electrons available in the conduction band and holes in the valency band. So hence intrinsic silicon must be modified by increasing the number of free electrons or holes to increase its conductivity. So this is done by adding impurities to the intrinsic material. So the conductivity of silicon and germanium can be drastically increased by the controlled addition of impurities to the intrinsic semiconductor material. So this process is called as doping. So that is by adding impurities to the pure semiconductor material, then we can increase the conductivity of the pure silicon or the germanium, and this process is known as doping. There are two types of extrinsic semiconductor, that is n type and the p type. Intrinsic semiconductor, so we will detailedly discuss about what is an intrinsic semiconductor and the eccentric semiconductor. intrinsic semiconductor. So it will contain all the either silicon or the germanium. So it is made up of only pure silicon or the germanium atoms. So you can observe each silicon, it has the 4 valency electrons and they will pair with the neighboring 4 silicon atoms to form one electron pair, and this electron pair is there in the covalent band. Is this electron pair is formed in the form of an one covalent band. So similarly, for any silicon atoms, the 4 valency electrons are shared by the neighboring 4 silicon atoms. They will form 4 covalent bands with the neighboring 4 silicon atoms. So at room temperature, at room temperature, all these valency electrons, they are tightly bonded with the neighboring silicon atoms. So no free electrons are available. So the intrinsic semiconductor, it will behave as an insulator. So it will behave as an insulator because no free electrons are available. So there is no current in the semiconductor. So this intrinsic semiconductor, it will behave as an insulator. So whenever if we apply any external thermal energy supplied, then the electrons gain energy and covalent bands will be broken. So whenever if you apply any external energy in the form of a heat, then these electrons, they will gain energy due to that heat and they will break this covalent band, and this electron, it will become free. So this is called it as an free electron. It is not bonded to silicon atom, so it is freely available. And whenever this electron is leaving from this covalent band, it will create one empty space or one vacancy in the covalent band, and this vacancy we will call it as an hole. So whenever if we increase the thermal energy, then more number of covalent bands are to be broken, so we will get more number of free electrons, and again these number of free electrons are limited. So we will get limited number of free electrons. So in the intrinsic semiconductor, it will carry current, but the conductivity is very less. So they can carry current, but that current capacity is very small. So in order to increase this conductivity, so we are using the doping. Then this is about the intrinsic semiconductor. So whenever one covalent band is broken, so we will get one electron and one hole. So in any intrinsic semiconductor, number of free electrons is always equal to number of holes. So if one covalent bond is broken, so one free electron and one hole is available. So if another covalent bond is broken, this electron will become free and here it will create one empty space. So now total 2 free electrons and 2 holes are available. So this is true for the intrinsic semiconductor. Number of free electrons is always equal to the number of electrons, the number of holes. So that is N is equal to P. N represents the number of free electron concentration. P represents number of holes concentration. And then we specifically discuss about what is a hole. So if I have taken one silicon atom, it is having 4 neighboring, it has 4 valence electrons. They will form covalent bonds with the neighboring 4 silicon atoms. So this silicon atom is sharing with one electron with the another silicon atom, so they will form one covalent band. So whenever we supply the thermal energy, this covalent bond to be broken, so this electron will become free, and while that electron, it will come out of this covalent band, and here it will create one empty space, and this empty space is called it as an hole, and this hole is not a physical particle. We are representing the hole as an empty space, so it is not a physical particle, it is only a concept to understand the empty space which is given as hole. And these holes, they are positively charged. Holes are positively charged. So this is about what is hole. So if any covalent bond is broken, one electron become free, so it will create one empty space in that covalent band. That empty space, call it as a hole. And these holes and electrons both move in opposite direction. Both move in opposite direction. So we will see. So in this structure, the hole is present in this covalent band. So any of these electrons, they will try to occupy this empty covalent band. So if this electron will occupy here, and this band will become completely filled, but in that electron where it is coming, so that will create one empty space here. Then again, in this covalent band, it has only one electron, so it is trying to occupy by the another free electron. So while doing it, so it will create an empty space in its position, and it occupies its in the another covalent band. So then again, this electron, again it is occupying this empty space, it is filled, but again in its original position it will create an empty space. So here you can observe the holes are moving from, so here you can say it is 1 2 3 4. Initially the hole is present in the covalent band 1. Now after occupying of these electrons in the covalent band 1, the hole shifted to second covalent band, then from second covalent band to the third covalent band and the fourth covalent band. So the holes are moving from left to right. Then similarly you can observe the electrons. So the electrons are moving from right to left. So you can observe the initially the vacancy is in the first covalent band. So the electrons are coming from the second covalent band. This electron is occupying this empty space which is available in the covalent band 1. Then again this in the covalent band here the empty space is available. This is occupied by the electron which is there in the third covalent band which occupying the empty space in the covalent band. So the electrons are moving from right to left. So both these electrons and holes they are moving in the opposite direction. And the next వచ్చేసి then electrons have the negative charge and their current direction is opposite of opposite to movement of electron. So similarly holes they are positively charged so its current direction is same as movement of holes. In whichever direction the holes are moving, so in the same direction current also moves. For the electrons it is in the opposite direction. So this is the basic difference between the electrons and holes. Then in the eccentric semiconductor these are formed by using fifth group elements. The pure semiconductor are added impurities of fifth group elements, then they are called it as an n-type semiconductor. So the silicon is the fourth group element and phosphorus is the fifth group element. So adding this phosphorus element to the silicon, then it will form an n-type semiconductor. So adding phosphorus to the pure silicon atom, silicon crystal results in a surplus electron and it will become free. So this phosphorus atom it is having 5 valency electrons and silicon has 4 valency electrons. So out of these 5 valency electrons of this phosphorus atom, they will form covalent band with the neighboring 4 silicon atoms. So because each silicon atom has only 4 valency electrons, it will form covalent bands with the 4 valency electrons of the phosphorus atom and 1 electron it is freely available in the semiconductor. So whenever we are doping with the fifth group elements, it will create more number of free electrons because one impurity atom gives one free electron. If the impurity atoms are increased, then we will get more number of free electrons. So in the n-type semiconductor, it has more number of free electrons. It has more number of free electrons because of fifth group elements. And these fifth group elements, they are donating one extra electron to the silicon or the semiconductor. So these fifth group elements are called as donor atoms. They are having total 5 valence electron and semiconductor has only 4 electron. So this extra electron, it is donating to the semiconductor. So the fifth group elements are called as donor atoms. This is the energy band structure for the n-type semiconductor. So valency band and the conduction band, and this is the forbidden energy gap, and here this is called it as a donor energy level. So it is nearer to the conduction band because this free electron, it is not bounded to any of these covalent bands. Whenever we supply energy of 0.01 electron volt, 0.01 electron volt for germanium and 0.03 electron volt for silicon, this fifth electron, it is easily moves from these donor energy levels to the conduction band. Then you can observe in the n-type semiconductor, we will get free electrons from the conduction band and from the valency band. So in the case of free electrons in conduction band for n-type semiconductor, they will come from two ways. One from donor level and the another from valency band. So the free electrons in the conduction band, they will come from two levels. One is from directly from the donor energy level, so which is requiring very small amount of energy in the range of 0.101 to 0.03, and another is from the valency band. So if any one of this covalent band is broken, then this electron also becomes free, and here it will create one empty space in that covalent band. So that's why the n-type semiconductor has more number of free electrons and it has very few holes. So the concentration of electrons is always greater than the concentration of holes in the n-type semiconductor. So this is how we can represent the donor atoms. So these are the donor ions, they are donating one electron. The minority charge carriers are the holes and the majority charge carriers are the electrons. So simply we can represent the n-type semiconductor by using these three: donor ions, free electrons and the holes. So the majority charge carriers in n-type semiconductor are electrons, minority charge carriers are holes. This is about n-type semiconductor. Next is p-type semiconductor. In the p-type semiconductor, the pure semiconductor is added or doped with the third group elements. Like boron. So boron has three valency electron. So boron belongs to the third group elements. It contains three valency electron. Silicon has four valency electron. So whenever this boron is sharing with the four neighboring silicon atoms, so three covalent bands are completely filled and one covalent band is empty. and that empty band, it has a deficiency of one electron, so that is represented as hole. The deficiency is represented as one hole. So adding boron to pure silicon crystal results in lack of an electron and it becomes a hole. So by doping third group elements to the pure semiconductor, it gives the p-type semiconductor. So for the p-type semiconductor, this is the energy band diagram. So valency band, conduction band, and the another is represented as acceptor energy level, which is nearer to the valency band because it contains the number of holes, so which is nearer to the valency band. If any electron from the valency band, it can jump to the acceptor energy level. For that, the amount of energy required is 0.01 electron volt for germanium, 0.03 electron volt for the silicon. By giving this much of energy, we can easily fill these holes which are available at the acceptor energy level by the valency electrons. So that's why the p-type semiconductor has more number of holes and less number of electrons. And these boron atoms, it is accepting one electron. It is accepting one electron. So these impurity atoms are known as acceptor atoms. These impurity atoms are known as acceptor atoms because one covalent bond is empty. It has deficiency of one electron. It is ready to take any free electron is available. So it is accepting one electron. So they are called it as an acceptor atoms. So this is how we can represent the p-type semiconductor acceptor ions. So because these are accepting electrons, so they will become acceptor ions. Then it has more number of holes and less number of electrons. So the majority charge carriers are holes and the minority charge carriers are electrons in the p-type semiconductor. So that's why the concentration of holes is greater than the concentration of electrons in the p-type semiconductor. Thank you.